Hello everyone. This is the third part of lecture number 2 in week 4, and it's a follow-on from the last lecture, part 2, where we talked about covariances. Probably one of the main reasons we talk about covariances is so that we can compute the mean, well, not the mean, but the variance of sums of random variables. So this part is talking about how to compute the variances of sums of random variables. Okay, so this section is called linear combinations, which is sums of random variables. We know that we often deal with sums in engineering. The load on the floor that you are currently sitting on is a sum of chairs, people, desks, computers, books, telephones, and so on, all of which are unknown or uncertain and therefore are considered to be random. To support this load, the engineer needs to account for the uncertainty in the total load, and the total load is a sum, of course. So basically, we need to know both the mean, standard deviation. We also need to know the complete distribution, but the most important thing is to get the mean and standard deviation. So to illustrate this, let's start with a simple sum and let y, our sum, be equal to a linear combination of two random variables x1 and x2. By linear combination, I mean the sum of the two, but possibly with some coefficients. So y is equal to a1 x1 plus a2 x2. To get the mean of y is fairly simple. We know that the expectation of the sum is just the sum of expectations. So mu y is the expected value. Y is the expected value of ax1 plus ax2. This is a sum, so it's the sum of expectations. So it's expected value of a1 x1 plus expected value of a2 x2. We know constants can come out front because expectation is also just a sum, and all of the terms in that sum are multiplied by a1, so we can bring it out front. And so we get the expected value of y is a1 expected value of x1 plus a2 expected value of x2. And that kind of makes sense. If you look back at this equation here, expected value of this thing is going to be a1 times the mean of x1 plus a2 times the mean of x2, which we get here. The variance is a little bit more complicated, but the rule is that the variance of a sum is the sum of all possible covariances, and we'll show that shortly. In our particular case, sigma y squared, variance of y, is the expected value of y minus its mean quantity squared. So this is the fundamental definition of a variance. But y is equal to a1 x1 plus a2 x2. So I can substitute y here with a1 x1 plus a2 x2, and I can subtract its mean, which we just computed up here, a1 mu x1 plus a2 mu x2, and then square the whole thing. If we look through this thing, we can collect terms. For example, the terms that involve a1 are x1 minus mu x1, so I got an a1 x1 times minus mu x1 plus a2 x2 minus mu x2 quantity squared. And now I complete the square. And I get the first term squared, a1 squared, x1 minus mu x1 quantity squared, plus this times this, plus this times this, plus this squared. And so I get these four terms here. And now this is of course, the expectation of a sum again. So the expectation of a sum is sum of expectations, so I can break it up at the plus signs. And I can bring the constants out front. So I got a1 squared, expected value of x1 minus mu x1 squared. And we know that this term here is just the variance of x1. And then I got a1, a2 times the expected value of x1 minus mu x1 times x2 minus mu x2. And this term is just the covariance between x1 and x2. The third term is a1 times the expected value of x2 minus mu x2 times x1 minus mu x1, and this is just the covariance between x2 and x1. We know that these two covariances are the same. Covariance between x1 and x2 is of course the same as covariance between x2 and x1. And the last term is just a squared times the expected value of x2 minus mu x2 quantity squared, and this thing is just the variance of x2. So we can say that this is the sum of all possible covariances. If we remember from the last lecture that the variance of x1 is just the covariance between x1 and itself, and the variance of x2 is just the covariance between x2 and itself. So we end up with covariance between x1 and x1, covariance between x1 and x2, covariance between x2 and x1, and finally covariance between x2 and itself. If I collect or simplify all these terms, I get a1 squared times the variance of x1, and I put these two together, 2a1 a2 times the covariance between x1 and x2, and a2 squared times the variance of x2. Another thing to note here is that all of the variance terms must be positive. Okay, so this thing here is a quantity squared, and this thing here is a quantity squared, so it has to be positive. But the covariance term can be positive or negative. As we saw in the last lecture, covariance can be negative or positive itself, depending on the slope of the relationship between x1 and x2. If it's negatively sloped, then the covariance is negative. If it's positively sloped, the covariance is positive. It also depends on the signs of a1 and a2. Okay, so some rules that come out of this, as we mentioned before, expectation of a sum is sum of expectations. In other words, if y is the sum of the ai xi's, then expected value of y is the sum of the ai's times the expected value of xi's. And the variance of a sum is the sum of all possible covariances. In other words, if y is the sum of ai xi, then the variance of y is the variance of this sum, which in this case is the double sum of all possible covariances. So I equals 1 to n, j equals 1 to, I forgot the n here. Let's put that in. Oops. N of all possible terms. And this relates back to what we had before. Up here we had, in this case, we had n is 2, so we were summing up two things. So we had a1 times the variance of x1, which is covariance of x1 with itself, a1 a2 times the covariance of x1 x2, a2 a1 covariance of x2 x1, and a2 a2 times the covariance of x2 x2. So that is a sum over I equals 1 to 2 and j equals 1 to 2 of all these possible pairs. So that's why we get a double sum when we add up all possible covariances. Another note is that if xi is independent of xj, then the rule becomes much similar. Because if xi is independent of xj, then the covariances all disappear if I is not equal to j. So the covariance between it, if x1 and x2 are independent, then covariance of x1 and x2 are 0. And so those terms disappear, and back up here, it means this whole centered term disappears. And I am left with just the sum of the two variances. So if the x's are independent, then the rule is much simpler. The variance of the sum becomes the sum of the variances. But I stress that this only happens if the variances are independent. So basically, anytime I'm looking at a variance of a sum, I ask the question, are those elements of the sum, are they independent? Because if they're independent, it makes my life a lot simpler. The variance of the sum becomes sum of the variances. So we'll illustrate this with an example. Let's suppose that the radiant energy that an object absorbs from a light source is equal to the source radiant energy times 1 over the square of the distance between the object and the light source. We know that this happens basically as the light radiates from a light source, its intensity decreases. And it decreases as a function of 1 over the square of the distance. Suppose that an object is illuminated by two light sources, A and B, with randomly varying radiant energies XA and XB. The object is 1 unit away from light source A and 2 units away from light source B. From measurements over a considerable time, it is determined that the mean of the radiant energy emitted by source A is 8, and its variance is 4. And the mean of the radiant energy emitted by source B is 12 with variance 9. And let's suppose that these two radiant sources have a correlation coefficient equal to 0.6. In other words, when one of them is stronger, it's more likely that the other is also stronger. So the question here is, what is the mean and variance of the radiant energy absorbed by the object at any random instant in time? So let's let dA be the distance from light source A and dB be the distance from light source B. If E is the energy absorbed, then E is equal to the radiant energy emitted by light source A divided by the distance squared, plus the radiant energy emitted by light source B divided by the distance to B squared. And if I plug in the numbers, I know that dA is, where's dA? 1, and dB is 2. So I've got XA over 1 squared, which is just XA, and XB over 2 squared, which is 0.25, or 1/4 XB. So I got an expression now for the radiant, for the energy absorbed by the object at any instant in time. If I look at now the mean of this radiant energy absorbed, it's just the mean or the expected value of XA plus 0.25 XB. And this is the expectation of the sum, which is just sum of the expectations. So it's the expected value of XA plus expected value of 0.25 times XB. The 0.25 is a constant. It can come out front. Oh, this should be, let me just correct this one too. Let's try this. This should be XB. Okay. And okay, so basically plugging in the numbers, we know the mean of XA is 8, and the mean of XB is 12, so it's 0.8 plus 0.25 times 12, which is 11, for the mean radiant energy absorbed by the object. Okay, the next question is, what is the variance of the radiant energy absorbed by the object? And we know from above that the variance is the sum of all possible covariances, since these are not independent. If they were independent, then this correlation coefficient would be 0. So I've got the covariance between XA and itself. I got the covariance between XA and, I'm just looking at this sum here, the covariance between XA and itself, the covariance between XA and this thing, which is 0.25 XB, plus the covariance between this thing and this thing, which is 0.25 XB, covariance between 0.25 XB and XA, which is this term, and finally the covariance between 0.25 XB and itself. These constants all can come out front. Okay, so we got covariance between XA and itself, which is variance of XA. We've got 0.25 covariance between XA and XB. We got 0.25 covariance between XB and XA, and these two things are the same. So I got 2 times 0.25 covariance between XA and XB. And finally I get the 0.25s both come out front, 0.25 squared, and the covariance between XB and itself is just the variance of XB. So finally I got the variance of XA plus 2 times 0.25 the covariance of XA and XB, plus 0.25 squared times the variance of XB. I know the first two things. The first thing, variance of XA, and the variance of XB. From above, variance of XA is 4, variance of XB is 9. But I still don't know this covariance. So I've got to work that out now. The fundamental definition of the correlation coefficient, rho AB, is that it's the covariance divided by the standard deviation of XA times the standard deviation of XB. Standard deviation of XA is the square root of the variance, which is the square root of 4, which of course is 2. And the standard deviation of XB is the square root of variance of XB, being the square root of 9, which is of course 3. Okay, so now I can solve this equation for the covariance of XA, XB by multiplying rho AB by these two things down here. Rho AB, I know the correlation coefficient is 0.6 times the square root of 4 times the square root of 9 is 0.6 times 2 times 3, which is 3.6. So the covariance between XA and XB is 3.6. And now I can plug that back into this equation up here, and I finally get variance of E is sigma x squared plus 2 times 0.25 covariance between XA and XB plus 0.25 squared sigma xb squared. and plug in the numbers, I get 6.36, so that my standard deviation of the energy absorbed is 2.52. Let me just go up and look at the expected value is 11, so we've got a coefficient of variation of about a quarter, 0.25. Okay, so that concludes the lecture about linear combinations. You'll see some examples and some questions about this coming up in your assignment and in the tutorial. Hopefully this will help clarify how to compute mean and variances of sums of random variables. Thank you.